All right, hello everybody. Hey, my name is Mike Davis. I am a software engineer at DoorDash on our data platform, and I'm also the tech lead for Apache Pinot at DoorDash. And so as part of the data platform, we own and operate Pinot for the rest of the organization, whether that's product teams or other data teams who want to build real-time analytics apps with Apache Pinot. All right, so let me just give a quick overview of some of these use cases that we have. And I'll start with monitoring our ETA models. So if anyone's familiar with the DoorDash app, while you're browsing through or checking out different restaurants, et cetera, you'll note that there's a time when that delivery is expected to arrive at your location. And there's a lot of details that go into how that number is computed, but what we're interested on the Pinot side is the performance of those estimations. Like how accurate is that ETA from the actual delivery time? So if we're saying it's going to take 25 minutes and it actually took 60 minutes, there might be something wrong there. And what we're trying to understand, is it a systemic problem? Did the models introduce some regression, or was it just kind of a one-off and just missed that particular expectation there? We also do a lot of experimentation at DoorDash, probably no surprise, but one of the things that is important with respect to the real-time nature of experimentation is are we actually reaching the audience or rolling out to the degree in which we think we are? So a lot of times with A/B testing, typically you're waiting days, maybe even weeks before you're reaching some sort of statistical conclusion. But in the meantime, you just want to make sure that, hey, how is my experiment tracking? Am I reaching, again, the audience that I'm expected? So this is another use case for Pinot, where the exposures of the individual experiments are ingested into Pinot in real time, and the various engineering teams that are focusing on these experiments can track that rollout. And then one more, ads reporting. So similar sort of motivation here. Want to monitor the efficiency of a particular ad campaign, how many clicks versus how many views for this particular ad. And this one actually is more of a customer-facing use case. The other two are more internal. But this one is actually driving some reporting within our portal application. Okay, so I mentioned real-time a couple times already, and of course, this is a real-time conference. So we have Pinot is both a offline and a real-time system. And just to kind of highlight this a little bit more, Pinot does have this notion of an offline mode. Well, I guess it's a little bit of a misnomer. So offline really in this case means the data is generated offline, like outside of the Pinot cluster. The data is like online, but it's not the responsibility of Pinot at this stage. We're in this model to consume the events, consume from maybe a data warehouse, consume from S3, and generate the formats that Pinot knows. So Pinot has its own proprietary columnar format that are formed into segments. And so in this mode, you typically have another set of services. It could be Spark, Apache Flink. Pinot also has a Minions framework as well. But these are batch loaded and typically scheduled. These are like hourly scheduled or daily scheduled. But again, the offline nature of this means that the servers themselves, so where the data resides, all you have to do is serve queries. So it's really easy. The relative workload on the servers is much less than the other table type, which is the real time. So again, the freshness on the offline table is going to be dictated by the cadence in which you're loading these tables. But on the real time side, this is truly continuous. This is now event level processing, where the servers in this case for Pinot are actually direct consumers upstream. There's no middleman in the process anymore. Pinot is connecting to your message bus of choice and has native support for Kafka, Kinesis, Pulsar. But it's important to call out the workloads are now extremely different. Now these servers have to not only ingest the stream, which could be very high volume, at the same time serving these queries. So, and doing so as soon as that message is received. So our freshness now went from hours on the offline side now to milliseconds and seconds on the real-time side. Okay, and here's a sample configuration. So we use Kafka at DoorDash, and a stream ingestion is effectively broken up into two different components. One is the consumer. It's like, where is this data residing? Like, what is that message bus, in our case, Kafka here? And then there's also a decoder side. So the decoder is like, now how do I interpret this message? So most of these message buses are effectively just transports of bytes, like bytes in, bytes out. They don't have a notion of the structure or form of the data. It's actually the responsibility of the producers and consumers to have this agreement. So go, okay, these messages I'm putting into this topic, they are of this form, and the consumers know that as well. Digging more into the consumer side, we do have, at least in the Kafka case, you would configure which topic to pull this real-time table source from. Is it a low-level or high-level consumer? I'll dive into that a little bit later. But it's also just important to note right here that we have a factory class name. So this is like the first time when you're configuring your table, you have to set up this factory class name, which is the package name of the Java class that is responsible for providing these particular implementations of the consumer. So right away, when we start looking at these configurations, we see that this is pluggable. This is something that we can actually probably implement our own if we need to. And maybe not, we might not have to, because there are a lot of native implementations. So on the decoder side, for example, we have JSON decoders, a couple different Avro decoders, CSV and protobuf, and each are going to have their own independent set of configurations. But that might not be enough. Maybe there's something going on with in your organization where we need to extend these or provide our own implementations. All right, so why would we need that custom decoder? So I guess taking it back a couple years, starting in 2019, 2020-ish, DoorDash made a big change from a monolith application into a set of microservices. So in that, we got a lot of benefits of that model brings. Teams were able to develop and ship more quickly. But we introduced this problem of, okay, how do all these services talk to one another? And for us, and a pretty common approach is to use protobufs and gRPC format. So protobufs give you this service level contracts. Like this, we can define what sort of endpoints are going to be available for this given service, along with the specifics of what a request payload looks like and what a response payload looks like. And this is a protobuf representation is a lot more compact than your traditional like JSON REST, so it's a lot more network efficient. So as part of this transformation from monolith to microservices, there's this like boom of protobuf adoption within the organization. All the services are speaking protobuf. Our real-time stream processing application built on Flink is also assumes protobuf as the message format. And the development of these convenience libraries for all of the application services are also kind of defaulting to protobuf. So the majority of messages that we're pushing into Kafka are using protobuf. So needless to say, protobuf was far more greater than Avro at DoorDash. And this is not typically the case for a data-centric platform organization. We typically see a lot more like Avro, but since we're coming from the microservices world, we kind of bled in a lot more protobuf adoption. Okay, so I mentioned we did have that protobuf decoder native in Pinot open source, so why can't we just use that? And when we look at the configuration, there's a few shortcomings. Well, first, this was introduced, I think, August of last year, so we've already were well on our way to needing something sooner than that. But looking at this implementation more recently, it's requiring the schema to be available on a file system somewhere. So typical approaches of a schema registry, where there's like a REST endpoint that you would use to like fetch that schema. We're not compatible with this particular implementation. So even though we're still making some progress, but we're not fully there yet. So we still have our own need for a custom decoder. Okay, so without this, if we said, you know what, there isn't this capability within Pinot, we actually are kind of just stuck with what's natively supported, we would have just a few other options that are like less than ideal. We could force our customers to publish everything in Avro, and we actually did that for a while. We said, hey, you want to use Pinot, you're on board right now, you're using protobuf, you're gonna have to convert that to Avro. Sometimes it wasn't a big deal because maybe there weren't very many consumers, and other times it was a blocker because there are too many consumers that are already assuming that this stream is going to be in protobuf format. So we could not, so that wasn't an option. So another solution, we actually never went this route because it was way too costly, but it came up. It's like we could just rewrite that same topic into another topic, just re-encode it for something that Pinot would support. But again, this was kind of heavy-handed, increased our operations quite a bit. The cost of running another streaming application plus maintaining that like large topic just wasn't feasible. And then the third one was just like, hey, so I know you want to do real time, but the format doesn't really work right now. How about offline? You just want to do that? Is that cool? And so none of these were that glamorous. It didn't really fit in with our like data platform model where everything produced and consumed within the data platform should be interoperable with one another. So then we went down this route of seeing how can we make the existing implementation compatible with our streaming ecosystem. So let me just touch upon the SPI here. So Pinot does support plugins via an SPI. And for the most part, the classes that we have available to us, they're just like Java interfaces, right? Where we define what a file system should look like, what a streaming consumer should look like, what a batch ingestion components should be consisted of. And this is all documented on the within Pinot's website. But just a quick definition here. What's the difference? Why are we saying SPI? What's the difference between API? Well, SPI is a service provider interface. And this is basically a lower level API that's like baked into the application, like this plugin style where it's not, these aren't like remote API calls. These are a contract within an application that can be extended. So we start with a interface, like an abstract interface, and then we would various implementations are then provided. So this has some of the caveats here is that you actually have to ship this with the application. This isn't just like another like microservice you can make external calls to. This is like embedded. And the contracts aren't as rigorous as they are with an external client API. Some of the documentation you gotta reverse engineer a bit, but the capabilities are there. So I mentioned that we needed the support for protobuf. We need to look into the stream ingestion SPI, and when based on the specification, it requires these 5 different implementations. But we're already I mentioned that we have consumers. So a stream ingestion is composed of consumers and a decoder. And for us, we're already talking to Kafka, right? So we can probably just reuse all the existing Kafka implementations, but we just need the decoder piece. So all right, so that's where we started. And kind of reverse engineering from the Confluent Avro Schema Registry decoder, we immediately came into a realization that the decoder interface only accepts a byte payload. So the byte payload is the value of the Kafka message. But Kafka messages actually have a couple more attributes. There is a wrapper consumer record that we have not just the actual payload, but there's a key that you might be using to partition your records within Kafka, and there's also Kafka headers. So Kafka headers, for those of you who aren't familiar, was introduced back in Kafka 11, and Kafka, these headers, these record headers, allow the injection of metadata for that individual record. So you don't need to, like in the previous example where the schema registry was using this like magic byte like header, kind of like hijacking the payload to like add some more metadata into the object. Now with the Kafka headers, it's a first class support for this additional metadata. And this is a string and bytes pair. And there are multiple keys that you can add. But I think the important thing here is that this is what we were using at DoorDash. So our client libraries that we use to enable the customers to easily push data into Kafka, we're actually using Kafka headers to inject a bunch of this metadata that we actually need on the consumer side to know how to properly deserialize this message. So basically that moved our implementation window from just having to do the decoder. Now we had to go deeper into the SPI specification and now somehow provide more than just the byte payload to our decoder. Okay, so, notice I'm highlighting the partition level consumer, but we also have the stream level consumer. So I'll talk about that in a second, but just a quick review. Kafka is a message bus. Think of it as a queue where we have the notion of topics. So kind of coming from the like pub sub type of terminology, where actually a topic is broken up into one-to-many partitions. So the number of partitions is assigned to each topic. Its base is relatively fixed. You can go up, you're not really gonna go down, but it's not a dynamic value. It's something you'd set based off of the size of your stream, size of your topic. And just to summarize what that means, if you have 100 partitions in your topic and you have 10 brokers in your Kafka cluster, basically 10 partitions are gonna be assigned to each broker in that scenario. We're ignoring replication, but that would just add another multiplier to this. But I think it's important to call out, this is how Kafka scales. This is how you can scale horizontally by adding more brokers and adding more partitions. We can actually distribute the load horizontally across the cluster. So then coming back to these two different consumer types, first the stream level consumer, or also called a high level consumer. This is has no notion of the partitions. It's just subscribing to a topic in the Kafka case. And so that means every single replica for a high-level consumer is gonna have to subscribe to the entire topic. So you can see this is probably starting to pose a scaling challenge. If we have a very large topic with a lot of partitions, that's probably gonna be overwhelming our servers. So instead, we also have this notion of a partition level consumer. So this is more analogous to how the brokers are being assigned the individual partitions. The Kafka cluster, the Pinot cluster as well, is going to be distributed, the number of partitions is going to be distributed across the number of servers assigned to that particular table. So here we have, and this is the case that we need at DoorDash. We have a large volume of events. They're not going to be able to be consumed by a single server. So then we need to implement the stream level consumer. The partition level consumer. And it actually didn't turn out to be too bad. So this is basically all we really needed to do. So previously in the default implementation, the consumer record is getting, the value is getting extracted out right there. So you see byte message. And that is what is actually being passed to the decoder. So instead of just passing just the byte payload, why not just pass the whole consumer record? And that's what we ended up doing. So so given that everything was properly encapsulated with generics. The original interface took bytes, assumed bytes, as the method signature. Now we can still use that same SPI. We didn't have to change the SPI at all, but the generic class just changed. Now the consumer record of string bytes is what we're using in this particular implementation. And now we have the partition level consumer. We can implement our decoder with that notion. Okay, so this is our kind of a pseudocode. There's more to it, but the idea is still there, where now when we call decode, and decode is supposed to return a generic row, that's Pinot's generic abstraction for what a row would look like, we now can check the headers and see, like, hey, how should this message be decoded? Should we use Avro, or should we use protobuf? And this is just a generalization then across like multiple different decoder types, and we can make that decision again based off of these Kafka headers. All right, so now we've shown how we can like build this asset. So based off of the SPI, we have the interface that we need. We can build our own implementation, kind of commandeering from some of the existing implementations, and we can build our own jar. We can build our own asset. But how do we deploy it? How do we get it part of the Kafka cluster? Because again, this is something embedded. And this is where Docker comes into play. And thanks again to all the effort that we did, in prior years to have a fully containerized deployment pipeline, along with a first-class Kubernetes cluster, we're able to, and the same sort of deployment model can apply for us on the data platform side that was being leveraged on the production application side. We can now bundle Pinot, actually just take the open source Docker image that is provided on Docker Hub, and we can inject add our own custom assets, in this case our own jar. So this has a lot of advantages. First, we're still leveraging all the assets from the open source community. We're not generating our own entire end-to-end pipeline, again, like replicating everything that is being done just to add this bit of functionality. Instead, we can use a layering technique within Docker. So there's a few more little bits in here, but for all intents and purposes, we're just taking two Docker images. One is just our builder. So our builder is just the Gradle JDK 11 builder image. So it's bundled with all the Gradle dependencies. And then we build our jar. And then after that, we take the open source Pinot image and then just copy that jar into the plugins location. So layering is awesome because it really speeds up your CI. Like, you don't have to, again, build everything from source. We're actually just leveraging the already containerized assets from Docker Hub and then just injecting our own implementation. And just need to be adding this jar to the proper location within the image. So if you ever just shelled into the image, there is a plugins directory where all of the other SPI implementations are stored, and everything in there gets automatically added to the class path. So the startup script within Pinot iterates through this plugins directory and adds all those jars to the class path. And so just hijacking that knowledge, putting our own image there. Now this is available to use within our own table configurations. And so I mentioned we're on Kubernetes. Typical deployment within Kubernetes is going to be using Helm charts. And a nice thing about a well-constructed Helm chart is going to be fully configurable. And the open source Helm chart for Pinot is no exception here. There is a repository field or a property and a tag property by default. Just going to be pulling the latest image from Docker Hub, but we can augment that with our own custom image that is in our own repository, and then we can actually like version our deployments. So latest is great for testing and iterating, but you'd really want to version your deployments in a production environment. That allows you easier roll back, and you're more confident of what is actually running within your cluster. All right, so now that we basically have our own custom plugin, we have a mechanism now to actually inject our own custom logic. And now these pipelines are already built and in production. Now, what else can we do with it? And we have already done some work on like unrelated to the plugin side, just adding more like custom capabilities to the Docker image is one pattern that we've exploited. But as far as this particular stream ingester, there's a couple of things that we like to do. Probably first on top of our list is to implement a dead message queue. So if you've used Pinot, if you use the stream ingestion mechanisms, you probably run into this before, where a bad message, maybe it's due to bad configuration, maybe it's a mismatched schema, but if the message can't be processed, you're basically stuck. You're basically blocked. So Kafka is, at the partition level, is you can think of as a FIFO. So every first message in, first message out, it's well ordered. So if you run across a message that you don't know how to handle, you're just going to be stuck there and keep trying over and over and over again. And you're probably seeing these graphs where like all of your partitions are the offset of your Kafka consumer. Everything looks great, it's all flatline, but then you have like one that goes off into the right because some bad message got in there. And so how do we deal with that? By default, it's just going to block. So you have a couple options. You can, if you're lucky, it might just be a transformation thing, a schema mismatch, and you just got to update your table definition, and then everything will continue on its merry way. But if it is actually a legitimate bad message, like how do you get around that? So there are some techniques to try like hack the offset within Zookeeper, stuff like that. Try to leave that to a last resort. And typically this comes in more on the staging side of things. So like while you're iterating and developing, maybe the customer is like changing their schema like rapidly. They're making some backwards incompatible changes because they use the wrong data type or something like that. And so if it's in staging, who cares? We can make backwards incompatible changes. But it still becomes like now a process. It still blocks in staging. So you'll have to drop and recreate the table. So dead message queue would be a better alternative. So if we detect that this message is actually wrong, let's publish it to another topic. Let's just like, instead of trying to like brute force hammer it home, we can publish it into another queue, skip it, and deal with it later if we have to. And so we can either, once it's in Kafka, we can write it out to an object store and recover that. Maybe it was legitimately a message that should have been processed. So we need to massage it a little bit to make it compatible. Or we can, it was something in testing and we can just ignore it. But so that'd be on the data lake side. But maybe even better is maybe we can just generically bring this back into Kafka. So one of the things, one of the models that we've tried to adopt more is like using Kafka to operate Kafka a bit. And this would be one of those approaches where that dead message queue we can generically define a kind of like an envelope schema, bring this into Pinot, and then use monitoring and on this topic to make sure that we're not throwing half of our messages away. So it allows us to kind of quality check this dead message queue while keeping the continuity of ingestion. Okay, another thing we would like to implement are some default transformations. So within protobuf, it's one of the data types that's commonly used is a timestamp field. It's like its own like wrapper object within protobuf that is composed of multiple fields, namely seconds and nanoseconds. And so what this means is, well, that's great for like RPC. So if you're getting this timestamp in your application, you can operate on it like a timestamp. That's great. But trying to ingest it into Pinot or any other downstream data store, like how are you supposed to serialize this into those stores? And so we in Pinot, we effectively have to flatten it out. And we have to do this a lot. So every single one of our real-time tables has this like kind of like boilerplate transformations where we are using Groovy to like flatten out the individual values from this timestamp abstraction. And it's just cumbersome, just room for error, something that we can just bake into the decoder. All right, so yeah, that's all I had. And yeah, just to highlight some of the advantages of this approach is we're able to provide our own custom logic without having to go through some of the more heavy-handed approaches of completely forking the open source repository. We don't have to build these assets from scratch. We don't have to continuously like merge in from upstream. We can just provide the logic that we need, ship that with the application with just kind of novel layering approaches, and that's it. Cool. So, willing to take any questions if you'll have any.
Are you guys planning to create like a design doc for the message queue?
Yeah, that is definitely something. Oh yeah. So the question was, the dead message queue, is there, should we be submitting a design doc to the open source community? Is this something that we can contribute back? And definitely something that I believe is generalizable, and something that we could add to the open source product. I think we'd probably like start internally, like see how this works, iterate on that design before then offering it. But it is generic enough where I think it could be possible. It could be a good addition. At the very least, a flag just to, hey, like, just skip it. Even like you don't even need the dead message queue part. Maybe that's a fast follow. At least being able to, hey, skip this if it's failing on some part of the transformation. Yes?
I came a little bit late. I may have missed it, but if I understand correctly, you're having this in the Pinot connector for Kafka, the decoder required.
Yes.
Have you thought about or considered doing it as an independent stream processor, for instance, and make it available not just for Pinot, for other services that they would like to have the message in the standard format?
Sure. So, well, the standard format is handled by our producer and consumer libraries, and so what we didn't want to do was add like another hop. So that added hop would not only contribute a lot more cost, but it also just in terms of cost of maintaining another topic, maintaining another streaming application. So being able to consume directly from Pinot was really the gap. So all the other applications spoke this format already. So we needed to make Pinot be compatible with our platform.
Pinot was the exception.
Pinot was the exception, right? One of the point on that. So one of the ideas is also like, hey, there's a Flink ingestion SPI, so or implementation where Flink can write segments. So technically we could, when we are power users of Flink. Most all of the real-time processing uses Flink. So we technically could consume from Kafka, done that transformation in the Flink layer, and then push that as a segment into Pinot. But then your downside is your freshness. So the advantage of the servers being direct consumers of the stream means they can serve the queries immediately as after acknowledging the event from the upstream queue. And I know I forgot to repeat your question, but yeah, the question was, why didn't we introduce another service in the middle between Kafka and Pinot, as opposed to embedding this logic into Pinot itself? Cool. Yes?
Have you done any benchmarking in terms of how your plugin performs versus with respect to the standard plugin?
We have not. So I guess if you take a look at the main decoder, it is effectively just doing a switch, like hey, use this decoder or use that decoder. So we didn't anticipate any performance issues, but we do monitor just the consumption rate, any sort of lag that would be produced. So if we were having performance issues, we would see that from the number of resources that we would have to keep up with the volume. And we haven't noticed any issues in that regard. It's a good question, though. Gotcha. Okay, thank you. So the question was around how we're managing our proto schemas, and we have any challenges with that with the plugin. So on the Avro side, we use schema registry, Confluent schema registry. And on the proto side, we're using a similar registry. It's not exactly the Confluent schema registry for proto, but it's very similar. And we have a dedicated pipeline for defining our protobuf definitions, and those get with CI/CD, those get published into concrete assets and then registered with the registry. So actually, one thing I kind of brushed under the rug is that the headers that we have tell us that it's a proto message, but actually it doesn't tell us where to look in the registry for it. So as part of the configuration, we do have an ID back to the registry. So the registry is used to dynamically fetch that schema. So if there is a schema change, we do have to bump the version within our config, but that's typically okay because we have to bump it anyway. So if you're adding a new field to the proto, creating a new version of the proto, you're going to have to bump the version of your table as well. So you're going to have to add that table to the table schema and update that. So those kind of go hand in hand. And since we do have schema enforcement within the CI/CD of the proto repo, then we know that all the changes are going to be backwards compatible. So if we are behind in the version, if a new version of the proto gets published and we don't release a new version, we don't increment our config, nothing's going to break. We just don't have access to those new fields.
You talked in the beginning about how the offline server is just responsible for holding the data and serving the queries, and the real-time servers have to do this consumption as well. Mm-hmm. Do you isolate your real-time and offline servers in your setup using tenant tags, or do you share those servers for both use cases?
No, that's a good question. The answer is yes. We do separate them using tenant tags because from Pinot's point of view, a server is just a server. That, whether it's offline or real-time, is a table-level config. So we do isolate the real-time nodes hosting the real-time tables independently of the offline tables. They're on a different set of pods. So, and we have seen read-write contention before we did that. So we didn't start out that way. We actually kind of just bundled like use cases together. So use cases from like one upstream or one particular product team are isolated from another product team. But even within them, there was contention on whether doing really heavy backfills or they had really heavy stream processing requirements or stream ingestion requirements. So to have more consistent I/O profiles, we'd separate those out. So yeah, for sure. What we haven't done is like really like custom tune those, like have different EBS types or different like storage requirements. Aside from like volume, like we'll give the offline servers maybe a larger disk than the real-time ones because typically the real-time are going to age out and in favor of an offline. I didn't get into hybrid tables, but that's a pattern that we use quite often where we have both a real-time and offline physical tables, but it's one logical table from Pinot's point of view. So like a lambda style architecture. Yeah.
If I recall correctly, we also had tiers on the different tiers of like criticality.
Yeah, so this was another convention that we adopted where actually the deployment of the cluster wasn't like one massive deployment. We actually broke it out into several Helm releases. So we would have like one set of default tenants that has your controller, because the controller is shared across the entire cluster, along with just a couple servers and brokers, really just for QA and testing. And then we'd have another Helm release or Helm version that actually disabled the controller. So we weren't just deploying the controller again because you want to do that. But then we would have different release semantics for that other like tier, we call it. So we would maybe have different alerting rules on this tier versus that tier, depending on the use case. And we can also do like staggered rollouts, because one bad thing about like one like Helm chart is everything's tied to one version, and you're effectively forcing the entire rollout of the cluster every time. But if you separate it out into multiple Helm releases, then you can actually stagger your deployments. Yeah.
Are you happy with Helm independently from the everybody is just as technology?
Am I happy with it? Yeah. So a question is, happy with Helm? Like it solves the need, but we ended up doing some like hacks like this. Like, hey, we'll actually have, instead of like one massive release, we'll have like 30. And I think the problem that with Helm is that you basically, if it's not a first class like parameterized value within the chart, then you're kind of stuck. You can't like configure something that isn't pre-made to be configurable. So that's been kind of problematic in the past, and we had to like go through iterations of the Helm chart, like update the version or add some more functionality to make that better. So it's gotten a lot better, but I know there's some configurations you want to set but aren't available in Helm, and then you either have to work around it or like vendor the Helm chart, and then now you're forking the Helm chart. Try to avoid just from a maintenance point of view.
How big is your biggest version?
How big is our biggest what?
Biggest version.
The values, yeah.
The values.
In the payloads?
The config.
The config for the Helm, the values for Helm.
How big are they? So I think our, maybe it's like 100 lines of customization. A lot of that is actually setting proper taints and tolerations to try to distribute the cluster across multiple AZs. So there's actually not that much customization of the chart itself, besides just like your resource limits and the size, and some like JVX settings or JVM settings.
We have time for one last question.
Okay. Yeah.
How do you do the plugin version management when you have to deal with multiple versions of the plugin?
So the question is how we do with plugin version management. So we bake. We haven't had. So we bake that plugin within our Docker image. So we release like a single version, a single asset, which is just the Docker image. So that plugin isn't available like outside of the Docker image. And if we needed to like roll back, we don't support running different versions concurrently. But if we did have to roll back, we just roll back the Docker deployment or the Helm deployment, or just change that tag. If we did have to support multiple versions, we would do so with like another class implementation, like a DoorDash StreamDecoder v2. Then you can actually support both of them. That's kind of like what the Kafka version, the native Kafka plugins have like two different versions that are concurrently supported. You just have to give them unique class names.
So you always make sure they're backwards compatible.
Yes, for sure. All right.
That is all the time we have.
All right.
Let's thank Mike.